These are the 5 cool ways on how birds evolved from dinosaurs. You can learn these 5 evolution ways if you watch this video till the end. 1. Feathers. The story of how birds evolved from dinosaurs is a fascinating tale of gradual transformation, and feathers played a starring role. Imagine a world millions of years ago, populated by small, agile theropod dinosaurs. These dinosaurs, ancestors of birds, sported feathers, not for flight, but for insulation. These early feathers were simple, downy structures, helping these dinosaurs stay warm in the cold. Over time, these feathers became more complex, evolving into the larger, more intricate feathers we see in birds today. Imagine these feathers gradually increasing in size and becoming more robust. As they did, they may have provided a slight lift, perhaps allowing these dinosaurs to glide from branch to branch, or even leap farther when hunting. This gradual development of feathers, coupled with other changes in their bodies, like lighter bones and wing-like forelimbs, paved the way for powered flight. The evolution of feathers from simple insulation to complex aerodynamic structures was a pivotal step in the journey from dinosaur to bird. It's a remarkable example of how nature, through gradual changes over vast stretches of time, can create astounding adaptations. Second wing development. The evolution of avian flight wasn't a sudden leap, but a gradual refinement of existing structures. Small, feathered theropod dinosaurs, ancestors of birds, possessed feathers initially for insulation or display. However, slight variations in feather length or arrangement could have conferred a subtle aerodynamic advantage. Individuals with longer feathers, for instance, might have experienced a slightly longer glide from branch to branch, improving their chances of survival and reproduction. This selective pressure favored the inheritance of traits enhancing gliding ability. Over countless generations, natural selection refined these advantages. Bone structure in the forelimbs adapted, becoming lighter and more flexible. Muscles developed to provide the necessary power for controlled movement. Feathers evolved into asymmetrical flight feathers, maximizing lift and minimizing drag. This wasn't a linear progression, but a complex interplay of genetic mutations and environmental pressures, with some lineages exploring different evolutionary pathways, some succeeding, others failing. The resulting bird wing is a testament to the power of evolutionary adaptation. It's not simply a modified arm, it's a highly specialized structure, a marvel of bioengineering honed over millions of years, a testament to the intricate dance between chance and necessity that shapes the course of life on Earth. 3. Miniaturization. The story of birds begins not with a giant leap, but a gradual shrinking. Among the larger theropod dinosaurs, a lineage of smaller feathered relatives embarked on a remarkable journey of miniaturization. Over millions of years, natural selection favored those with slightly smaller bodies. Why? Smaller size unlocked new ecological opportunities. While larger dinosaurs competed for large prey, smaller ones could exploit insects, seeds, and fruits hidden in dense vegetation. Their nimbleness allowed them to escape predators more easily and navigate complex environments. This shrinking wasn't just about survival, it was about flight. Powered flight demands a precise balance between wing size and body weight. The lighter frames of these shrinking dinosaurs made the development of wings and the transition to powered flight far more likely. This miniaturization, therefore, wasn't a side effect. It was a crucial step, paving the way for the incredible diversity of birds we see today. It's a testament to how seemingly small changes can have profound evolutionary consequences. 4th, skeletal changes. The evolution of birds from dinosaurs wasn't just about feathers and wings. It was also about a remarkable transformation of the skeleton. Picture a small, feathered dinosaur, its forelimbs still more arm-like than wing-like. Over millions of years, these bones underwent a series of changes, driven by natural selection favoring those individuals better suited for gliding and eventually flight. Bones in the wrist and hand became more flexible, allowing for greater range of motion and control. The shoulder joint became more robust, capable of supporting the powerful muscles needed for wing movement. The bones in the forelimbs themselves became lighter and hollow, reducing weight without sacrificing strength. This streamlining of the skeleton was essential for achieving powered flight, allowing birds to take to the skies with greater ease. These skeletal changes weren't isolated events, but part of a complex interplay of adaptations. The evolution of flight feathers, the development of powerful flight muscles, and the reduction in body size all contributed to the emergence of birds. The bird skeleton, a marvel of engineering, is a living testament to this long and intricate evolutionary journey. Pieta paedomorphosis. Imagine a baby dinosaur. It might have relatively large eyes, a short snout, and a proportionally larger head compared to its body. Now imagine that, over generations, some dinosaurs retained these juvenile features even as they grew to adult size. This process, called paedomorphosis, played a significant role in the evolution of birds from dinosaurs. In essence, birds evolved by retaining certain juvenile characteristics of their dinosaur ancestors. These features, which were advantageous for young dinosaurs, became permanent traits in adult birds. For instance, the large eyes and short snouts of baby dinosaurs, useful for navigating their environment and finding food, were retained in birds, enhancing their vision and sensory perception. This retention of juvenile traits, while seemingly insignificant, allowed birds to develop unique adaptations, like the ability to see a wider range of colors and detect rapid movements, which contributed to their success. Paedomorphosis, therefore, was a critical factor in the evolution of birds. It allowed them to retain features that were advantageous in their juvenile stages, leading to the development of unique adaptations and ultimately contributing to their remarkable diversity and success in the world today.